Hello everyone, I am pleased to present our work, Token Downsampling for Efficient Generation of High-Resolution Images, work done by myself, Nayana Saxena, and Ninda Saha of Leonardo AI. For some background, I'll take a moment to talk about transformers and attention networks, both of which have been critical to the success of the explosion of generative models recently. Specifically, language models and diffusion models often use attention networks where either words or pixels will be treated as tokens in a sequence. We know that attention over long sequences is expensive due to the quadratic scaling. Images specifically are quite high dimensional, and this will result in very long sequences. Specifically for Stable Diffusion, a 512 image, even in latent space, at its highest resolution part in the network, will give you a 4,000 token sequence. Attention is sparse, and it can often be well approximated by cheaper options. We have seen things like the focal transformer or neighborhood attention methods that aim to use only surrounding tokens to attend to, eliminating the O(n)to scaling. And then there's other methods that attempt to remove the softmax and linearize attention such that it can be done more efficiently. However, these methods typically require training time modifications as well to leverage our speedup. As we'll show, our method can be applied out of the box. A similar method to ours, token merge, reduces attention tokens by merging tokens with the highest similarity. However, to actually get the similarity in the first place, you have to calculate the similarity matrix, which is still O of n squared. Secondly, because you are at any time because when these tokens are merged, you want to keep the size of the image constant. You then have to unmerge the output of the attention layers as to keep the image size constant throughout the network. And that can be almost the equivalent of upsampling an image after downsampling, and that can hurt quality. We noticed some things that, for example, nearby pixels in images tend to exhibit similar pixel values, so we question whether the same might be true for features in the UNet, that the most similar tokens may be nearby as well based on contiguity. Secondly, the merge-unmerge operation comes at a cost to quality. We wonder if reducing the context tokens, exclusively the key and value tokens, rather than the whole set, can allow us to retain quality while still maintaining similar speed. So we introduced token downsampling. We will reduce the number of tokens used in attention with a low-cost downsampling operation. It's equivalent to just subsampling the grid of tokens or pixels when you choose the nearest neighbor algorithm, which we use for our comparisons and focus of this paper. Additionally, we choose to only merge the keys and values, so then we avoid having to ever unmerge. We show either comparable speed or faster compared to token merge, showing results at 1024, 1536, and 2048, where as we get to higher and higher resolutions, the gains become more substantial. We show greater fidelity towards the baseline output, evidenced by reduced mean squared error, and lower or reduced loss of high frequency details, which we show by running a high pass filter over the output and extracting the mean magnitude of the resulting output. Here we have results at 1024 by 1024. At baseline, 8.8 seconds versus ours, 5.8 seconds. This is done with a downsampling ratio of 2, otherwise removing 75% of the total tokens in the image. You can see that token merges method comes at expense of details in the face and blurry backgrounds. At 1536, we see 44 seconds for baseline, while 14 seconds for our method. Now even beating token merges time. and still token merge suffers from loss of details and some artifacts in the faces as well. We also investigate the features within the unit to explore our hypothesis that nearby tokens exhibit redundancy, informational redundancy. To look into this, we check the normalized cosine similarities between surrounding tokens in a 3x3 neighborhood, specifically here at 1024, 1024. We see that the neighborhoods of tokens exhibit very high similarity, where we actually plot the lowest similarity in that neighborhood to show the sort of a upper bound to the information loss you would have when removing these tokens, basically. And we see that these similarities decrease throughout the generation, starting at very high in the beginning when the image is still noisy. We suspect as in the beginning of the generation, the content spatially is, I suppose, a little blurry, whereas later on the details become more and more differentiated. In conclusion, token downsample achieves competitive speed at reduced distortion compared to the previous works. We find some early evidence for informational redundancy in the features of the unit. As future work, we will seek to attempt training a model with token downsampling to achieve generation at resolutions previously not possible, and conduct further investigations into informational redundancy within the unit. I will also show a quick demo here. We build off of the original code base provided on the token merging such that we preserve their original implementation as well. So, and as noted, we use the Dream Shaper model for all experiments as it is a publicly available model and it handles larger resolutions better out of the box, which is our main focus here. So we will attempt a generation now with baseline. And it finished at 91 seconds here. And this is the output. And then next we will do the original method of token merging. Similarity, we will merge such that only roughly 6% of the tokens remain. Otherwise, 93.75% tokens are removed or merged away. It is set to merge all tokens as opposed to just the keys and values. And these are not relevant settings for what we're currently doing. So this is the output from the token merging method at 21 seconds. And then now here is our method at the downsample factor of 4, which downsizing the image by 4 is equivalent to removing 93.75% of the tokens. And you can see as well 1.46 steps per second, total of 18 seconds to finish. And this is the result, adhering quite nicely to the original.